This is part 2 of lesson 2, part B. And what we're going to be discussing is a process of using logarithmic differentiation. Example 1. As you can see here, we have a function that has a variable to a variable. That's what makes this different. It's not like y equals, let's say, x to the power of 5, where we would use the power rule and bring down the 5, x to the power of 4, nor is it something like 5 to the power of x, which you might know as a to the x. So this one here is different than that. And this is the classic example where it's x to the x, variable to a variable. Okay, so let's begin and figure out how to find this derivative. Here we go. So the process. The first thing we want to do is take the natural log of both sides. So we have the natural log of y equals the natural log of x to the power of x. But we're going to use a property of logs like we did in the first part. So the natural log of y is x times the natural log of x. Now we're going to take the derivative of this relationship with respect to x. And we have the derivative of natural log of y equals the derivative of x times natural log of x. And we're going to employ implicit differentiation. So the derivative of natural log of y, or natural log of stuff, is 1 over stuff times the derivative of the stuff dy dx. On the right-hand side, we have a product, so we're going to use the product rule. First term, x, times the derivative of the second, 1 over x, plus the second term, natural log of x, times the derivative of the first, times 1. So here we have it. So now we have dy dx equals, and the key part here is to multiply both sides by y. So it's y times x over x plus natural log of x, or simply stated, dy dx equals y. Now we know what y is. It's defined earlier to be x to the power of x. Now I'm simplifying this expression, and we have dy dx, which is what we desire to find when y equals x to the power of x. Let's take a look at the second one. Here we have y is x to the power of tangent of x. Again, our desire here is to find dy dx. So first thing is, we're going to take the natural log of both sides, natural log of y. The tangent of x becomes the exponent that gets pulled down, tangent of x times natural log of x. And we do the derivative of the relationship with respect to x, and tangent, a funny looking tangent of x, times the natural log of x. And here we go. So 1 over y dy dx. Again, the natural log of stuff, 1 over stuff times the derivative of the stuff, equals first term, tangent of x, times the derivative of the second, 1 over x, plus the second term, natural log of x, times the derivative of the first. We must make sure we have these memorized, secant squared of x. Okay, jump down. Key element to this now, dy dx, again, is to multiply both sides by y. So we have the tangent of x over x plus natural log of x times the secant squared of x. And we have to make sure that we make our original substitution. So the original problem was x to the tangent of x times tangent of x over x plus natural log of x times secant squared of x. And we can leave it just like that. And that is the process of logarithmic differentiation, and very important part of the section. The end.